Okay, we're gonna do the next part. We're gonna talk about the gravity at a distance, the inverse square law. Let me dismiss my image so I don't interfere with the PowerPoint. The inverse square force law applies to a force magnitude which varies as the inverse square of the distance from the source of the force. And we'll see that, well, you may not see it, but it applies in several instances. Certainly the gravitational force obeys the inverse square law. Electromagnetic force, the force that attracts a electron and a proton is obeys the inverse square law, and it doesn't work with magnets. Magnets attract each other, but there's more dynamics going on in magnetism that it doesn't apply there. But those are uh, two instances of the inverse square law. In a equation form, the force is proportional to 1 over the square of the distance. So as the distance gets uh, uh, farther, the force diminishes uh, by a square term. So if you double the distance, you've cut the force by 1/4. If you half the distance, you've multiplied it by 4. At greater distances, there is a smaller force. Even at great distances, force approaches but never reaches 0. So in theory, the Earth has a gravitational pull on um, now Pluto's not a planet anymore. It's called a dwarf planet, but conceptually the Earth pulls on Pluto. Now it's a very very weak force, but the concept is that it's not 0. Um, okay, let's now here's a kind of an example. Let's say you have a can of paint, and as you spray this paint, let's say you have a little plaque and you spray it here, you get 1 layer thick. As you increase the distance on a different plaque, it's 1/4 layer thick. You've got 4 times the area, and if you triple it, well, it's 9 times the area, and you quadruple it, well, now it's 16 times the area. Oh, I guess you were supposed to fill those out. But so this is 9 area units. This is 16 area units, and these would be 1/9 layer thick and 1/16 layer thick. So that's how the inverse square law works. And here it is graphically. You can see how the gravitational force on the Earth is very very strong. As you move further out, it becomes weak. Now the space shuttle. Well, maybe I should say that for later, but not really. I mean, at the distance that I said space shuttle, where the space shuttle doesn't run anymore. The International Space Station is what I should have said. The International Space Station, as high as it is above the Earth, we see the astronauts on the International Space Station, and they look weightless. So we figure, oh, there's no more gravity up there. No, there is. There's about 94% of Earth's gravity is still in effect. It's just that the International Space Station is actually falling, and I'll show you that a little bit later. Okay. Let's see. The force of gravity between 2 planets depends on their masses and separation distance, planetary atmospheres, rotational motions, all of the above. Well, if you look at the formula, F equals G M1 M2 divided by their distance squared, it's only the masses and the separation distance. According to Newton's universal gravity theory, The gravitational force between two objects depends only on the masses of the objects and their separation distance. Other factors such as atmosphere and rotation are irrelevant. They don't count. Okay, if the masses of two planets are each somehow doubled, the force of gravity between them would be, well, you would have G m1 m2 over d squared. Well, if now it's 2m1 and 2m2, now that's a quadrupling. That's a multiplication by 4. So it would be quadruples. Note that both masses double, then the double times the double is a quadruple. Okay, if the mass of one planet is somehow double, the force of gravity between it and the neighboring planet whose mass does not change, it would only double. You have m1, m2. If now you have 2m1 times m2, it would only be a doubling of the force. Let the equation guide your thinking. Note if one mass doubles, then the force F equals G m1 m2 divided by d squared. It just doubles. So if you're just doubling one of the masses, then the force just doubles. Okay, and that's the end of part 2, and we'll continue with part 3 in the next video.